Hello and welcome to this lecture. In this lecture, we're going to do a whole bunch of problems involving e power x. Okay, so far we have not had this function e power x, right? In this course, it's been so many weeks. We have dealt with the polynomial function, rational functions all the time without having a powerful function like e power x in our hands. Now we have e power x. What can we do with it? How do we analyze it? How do we picture it? How do we do various things with it? Okay, so we're going to do that now and explore this function e power x in more detail. Okay. So first question asks you to plot and describe how these various functions will look. Okay, 1 by 1 plus e power minus x. Okay, so the way to understand functions usually is to look at their values for various different values of x, and you can maybe connect them. You know, these functions are going to be all continuous, all differentiable, very smooth, and all that. So you can just evaluate it at a few points and see. But it also helps to know that e power x is growing exponentially with x and e power minus x is falling exponentially with x, right? So these kind of properties are important to know, and when x goes moderately large itself, e power minus x will become really small. Okay, so for instance, if you look at 1 by 1 plus e power minus x, for x positive, x equal to 0, I'm getting half, right? If x is 0, this function is half, and as x goes positive and keeps increasing, I'm expecting this value to become really small. If it becomes small, this is going to go off to 1, right? 1 by 1 plus e power minus x will quickly go off to 1. So it starts at half at 0, and then it will quickly go off to 1. At the same time, if x is negative, e power minus x is blowing up. It's becoming very big very quickly. So this whole thing will go off to 0 very quickly, right? So this 1 by 1 plus e power minus x is this very interesting function. Sigmoid function. It has a lot of names. It's used a lot today in machine learning and all these things. So it starts at 0 for negative x, it's at half for x equals 0, and goes to 1 for positive x very quickly. Okay, so you can plot this. Let's try and plot it. I'm trying to get a Desmos here, so I'll have to get another tab for you. Let's do a graphing calculator. So Desmos can do exponential very well, 1 plus e power minus x. Okay, notice this function is exactly what I told you would happen here. At 0 it is half, and as x becomes negative, it's quickly going down to 0 by minus 4, minus 5 and all. It is already at 0, and at plus 4, plus 5, it is going off to 1, right? So this value is 1 and all. So if you want, you can zoom in a little bit and then see that, you know, at around 5, 6 and all, it's gone very close to 1. At minus 5, minus 6, it's gone to 0. So this is called the sigmoid function. So notice how we are able to construct these kind of functions. You can't do this with polynomials and rationals and all that, right? So you can really control, you know, this is also, it's a very smooth function. It can be differentiated any number of times. So if you want to find the maxima, minima, you can use differentiation. All those things it plays very well with. Okay, so here is first example of a function that we saw. Okay, the next function that you are asked to analyze is this one. Look at the behavior: e power x minus e power minus x divided by e power x plus e power minus x. The first thing you're worried about when you have a rational is denominator should not become 0. But in all these cases, denominator will never be 0 because, right, e power x is positive, e power minus x is positive. So this is not, there's no danger of going to 0. But let's just evaluate what happens. Once again, x equals 0 is interesting. At x equal to 0, you get 0, right? Because it's 1 minus 1, numerator goes to 0, so you get 0. What happens for x being very large? As x increases in the positive direction, not even very large, moderately very large x, right? Because of this e power x property, e power minus x is going to be much smaller than e power x, right? E power minus x is going to be much smaller than e power x. So if x is positive, even for moderate values like 5, 6 and all, I'm expecting e power x to dominate over e power minus x. So numerator will roughly be e power x. Denominator again will roughly be e power x. So as x becomes moderately high, 5, 6 and all, I'm expecting this ratio to become 1 plus 1, e power x by e power x. What happens in the negative direction? As you go to moderately high values, e power minus x is going to be very large. On the other hand, e power x is going to go to 0, right, if x is negative. So I expect the numerator to be minus e power minus x. I expect the denominator to be plus e power minus x. So it goes to minus 1. Okay. So this function seems to be sort of similar to this function, right? This function went from 0 to 1 with half at the center, at 0 at the origin. So here it will be 0 at the origin. It's minus 1 for x being negative and plus 1 for x being positive. So this is actually called tan hyperbolic type function. It's related to that. Okay. Apologies. Let's go to Desmos and we'll plot this guy. Y equals e power x minus e power minus x. I have to put, do I need that or put pi, what will happen? Okay. Pi e power x plus e power minus x. That is the blue function. Oh, sorry, I put e equals, apologies, y equals. Okay, so that's the blue function. Contrast it with the red function that we have before. It's at minus 1 to plus 1. Notice that it's how come that this function seems to be hitting minus 1 much faster and plus 1 much faster? Not much, a little bit faster. Because see, here you had to compare with 1. Here you are comparing with e power minus x. E power minus x is falling, e power x is blowing up. Here only e power minus x is falling or blowing up, 1 remains 1. Okay. So this one is a little bit better than 1 plus 1 by e power minus x in terms of how quickly it reaches the final value. So notice these kind of wonderful functions, right? Minus 1 to plus 1, very smooth, no problem. You can create all these kind of interesting functions using exponentials. Without exponentials, these kind of functions really will not be possible. Okay. So let's go to the next function. Next function is x times e power minus x, x squared times e power minus x for x positive. We're going to look at x positive, x negative, it will go a little bit bizarre. So what's happening once again here? X is a function which increases with x, right? It's just linearly increasing. E power minus x is falling exponentially. So when I multiply these two, because exponential fall is faster than any kind of polynomial x or x square growth, I eventually expect it to go to 0. But initially what will happen? Initially this x will assert itself, right? It will slowly increase from 0 and then it will fall. Same thing will happen to x square e power minus x. It will increase from 0 and it will fall. Okay. To plot these things and observe the behavior once again, let's call on Desmos. Maybe we can disable these two, we don't want these guys. I'm going to do here y equals x power n times e power minus x. And I'm going to add a slider for n here. Okay, it starts at 1 and I don't want to distract myself with x negative, so we'll just do x positive. Okay, and then notice the slider, let's start at 1 and it goes to 10. Okay, so as I keep increasing, notice what happens as n increases. So does this make sense? If n becomes 3, for instance, the peak is shifting to the right. So it's growing initially and then eventually it's falling. E power minus x will assert itself, but initially because of the x cube growth, it grows and then it falls, right? So that's the behavior, and you can do all this quite easily, and you can see how it works. Maybe we can zoom out a bit and then make a video here. Ooh, look at that. It's always going off to 0. If you want to see it very much, you'll have to zoom out a lot. Look at that. See, it's always falling down, but then the zoom out picture is not looking very nice, isn't it? So you can see the zoomed in picture a bit here. Maybe you can see something. Hopefully that gave you a good idea of how that works. Okay, so this is how these functions will behave. Okay, so that's going to be x e power minus x square e power minus x. Here's another function, e power minus x squared. Wow, it's a bit scary, isn't it? So minus x square is showing as the exponent of e. Okay, so let's look at what happens when x is 0. X is 0, this is going to go off to 1, isn't it? So x is 0, it's 1. If x goes positive, I'm having e power minus x squared, which means x goes positive when large, e power minus x squared will go off to 0 very rapidly, right? Isn't it? It starts at 1 and it will go off to 0 very rapidly because x is x squared even, right? If x goes to 2, 3 and all, it's e power minus 8, minus 9, like that, it just falls off rapidly. What about x being negative? Even if x is negative, x squared is positive. So this function e power minus x squared is going to have a peak at 0 and it's going to fall on both sides in a sort of symmetric, nice fashion. It will fall, and in fact you will get this very famous bell shape. Okay, so let's look at this. Let's teach this guy also, and let's just do y equals e power minus x squared. Okay, my scale is a bit off. Let me just do the home picture. So there you get the whole shape. Okay, this is the famous bell shape. You can zoom a bit, or maybe you can shrink it if you like. You can change this x squared. I can put a little factor here and add a slider here. And if I put a positive and start with 0.1, sorry. So if a is going to be, if I increase a, the bell becomes sort of more bell-like, it becomes narrower. And if I decrease a, it becomes more of a shallow growth. Okay, those things make sense, right? Ax squared, if a becomes larger, ax squared is blowing up faster, so this will just shrink quicker, and this is how it will go. So you can see this, see how this behaves. Notice how this whole plot is becoming flatter and going on. Okay, so this is a very, very famous bell shape. Again, these kind of shapes are impossible to get with polynomial functions in a smooth way, right? Smooth, differentiable way. It's differentiable as many times as you like, and it has this wonderful behavior. It's exponentially falling down e power minus x squared behavior. This is a bell shape. Okay. Okay, so that's just behavior. So you can imagine many other type of functions you can create like this with the exponential function. Okay. So now limits with exponentials. Okay, so far we have never had limits with exponentials. Here is limits with exponentials. Okay, so how do we do limits? Look at the first limit. Very, very interesting limit. It says limit as extending to 0 e power x minus 1 by x. Here you have, what is the numerator if you put x equal to 0? You get 1 minus 1, 0. What is the denominator if you put x equal to 0? You get 0. So you have a 0 by 0 form, and you're taking limit as extending to 0. So how do you resolve a 0 by 0 form in the limit? You use L'Hopital's rule. If you use L'Hopital's rule, what will happen? Let's see that. Limit as extending to 0 e power x minus 1 by x. You can use L'Hopital's rule. It's the same as derivative of e power x, which is e power x itself. Minus 1 will go off to 0, right? So the derivative is just e power x divided by 1. And now we can evaluate. The limit is 1. Okay. What a wonderful clean limit. E power x minus 1 divided by x has a limit of 1. The other way to see it is e power x is 1 plus x by x squared by 2 factorial, x cubed by 3 factorial, so on. E power x minus 1 divided by x is actually 1 plus x by 2 factorial, x squared by 3 factorial, plus so on. Okay. And if you put x equals 0, limit as extending to 0 of e power minus x by 1 is the same as putting x equal to 0 here, and you get 1. These are two ways of proving it, one using the series, one using L'Hopital's rule. Anything is fine as long as you get to the correct answer and the limit is 1. Okay. What about this guy here, e power x minus 1 minus x divided by x squared? You have to use L'Hopital's rule twice, or you can use the same series type expansion I showed you. I believe you will get the answer as half. Okay. So answer will be 1 by 2. You can check it. Let's come here. Okay. This is sort of like the tan hyperbolic function, right? So a e power minus x plus b e power minus x divided by e power x plus e power minus x. Not really tan hyperbolic, sort of like that. Okay. Now x tending to infinity, what will happen? When x tends to infinity, e power minus x will go to 0 and e power x will cancel and you'll simply get a. Okay. So this is a function which goes to a as x tends to infinity. What happens when x tends to minus infinity here? Right? If x tends to minus infinity, e power x will go to 0 and e power minus x will cancel and you will get b. So, this is a function which sort of is at b at minus infinity and it goes to a at plus infinity, and it is moderately quick, no, this kind of growth is quick. So, it goes from a to b instead of from -1 to 1, which is for e power x minus. So, this if you put a equals 1 and b equals -1, you get this function, right. So, this guy is a special case of this one, okay. This is what you get. Here's another limit you can evaluate with e power x. Here is where this x power n comes in. As x tends to minus infinity, 2 plus x power n e power x. When x tends to minus infinity, I know even though this x power n is blowing up, e power x will smother it, right. So, this will go to 0. This limit will simply be 2. Okay. So, this other guy will go to 0. Okay. So, those are the first two type of functions where you could take limits. You can now what will happen is any limit problem you have, we can throw in exponential functions. So far we have not done limits with exponentials. Now, if you bring in the exponential function also, you can do the limit quite easily. Okay, hopefully you can see it. You just have to use the facts about what happens to x, e power x. As x tends to a finite value, it goes to some proper finite value. If x tends to infinity, e power x goes to infinity. X tends to minus infinity, e power x goes to 0, and e power minus x behaves in a opposite manner. Okay, so use those ideas, you'll get it. So, the third problem asks you to find the maxima and minima of the following functions. So, these functions are smooth, they are differentiable. All you have to do to find maxima minima is differentiate, equate to 0. Okay. So, that's the way to find critical points, right. So, once you find critical points, you can do something. So, let's quickly do this. X power a e power minus bx. Okay. So, you have x power a e power minus bx. Did I get that right? Yeah, everything is positive here, x is positive, that is what we are interested in. So, if you do a derivative, you have to use the product rule here, right. I am going to say x power a times the derivative of e power minus x, that is minus b e power minus bx, plus x power a derivative, which is ax power a minus 1 times e power minus bx, and this has to be 0. This is the critical value. These are the values where peaks or troughs happen. Okay. So, here if you see e power minus bx and x power a minus 1 can be pulled out as common, right. So, x power a minus 1 times e power minus bx times you will simply have here x power a minus 1 goes. So, you will only have x and then minus b will be there. So, minus bx plus a equals 0. So, this quantity becomes 0 only when x is 0, and I am looking at x being greater than 0 generally. So, this quantity is not equal to 0, right, for any x positive. So, only way this can be 0 is x equals a by b. Okay. At x equal to a by b, this function x power a e power minus x reaches a maximum or a minimum. Okay. We know that this is going to reach a maximum, no, just given the behavior, we have seen these kind of plots before, but in case you want to check if a by b, if it's going to be positive or it's going to be, is it maxima or minima, right, that's the next question, no. Maximum or minimum. Okay. So, it turns out in this case it's a maximum. Okay. So, you can argue this in many ways. You know x power a increases, e power minus bx decreases. So, this will increase and decrease. So, that is one very intuitive way of arguing for the maximum. Another way of doing it is to check what happens to f prime of x. Okay. So, this is f prime of x. Suppose f of x is x power a e power minus bx. F prime of x is something we did just now, x power a minus 1 e power minus bx, which is always positive, times a minus bx, isn't it? This is what is f prime of x. Now, around a by b, if you say around a by b, if x is less than e by b, this is greater than 0 if x is less than a by b, and it is less than 0 if x is greater than a by b. Okay, so this is very important to know. So, if x is less than a by b, this a minus bx is positive. If x is greater than a by b, it is less than 0. So, what is happening to the derivative? Derivative is positive here, derivative is equal to 0 here, and derivative is less than 0 here. Okay. So, the function is increasing to the left of a by b and it is decreasing to the right of a by b. So, clearly this will be a maximum. Okay. So, this is how you figure out whether it is just calculus wise figure out. Another way of doing it is you can differentiate f prime twice. If you differentiate it once again, you are going to get x power a minus 1 e power minus bx times minus b, right, that is the derivative here, plus this a minus bx times the derivative of a power x power a minus 1 e power minus b. So, you do not need to bother about the derivative. If you evaluate f prime at a by b, this quantity will be something, but it will always be positive, some positive quantity, times minus b plus 0, right. So, this goes off to 0, isn't it, equal to 0 if x equals a by b. So, this does not really matter. So, the double derivative is negative. Okay. So, this is called the double derivative test. If you want to find out if a critical point is maximum minimum, you take the second derivative test. If second derivative is negative, this implies maximum. What is the meaning of second derivative being negative? It means first derivative is notice what is happening to the first derivative. So, this is f is increasing, f is decreasing. Okay. What is about f prime? F prime is positive, f prime went to 0, f prime became negative, which means as you go here, f prime is decreasing at a by b, right. At a by b, f prime is a decreasing function. No, it is greater than 0 for just to the left, at 0 at a by b, and it is negative for x greater than a by b. So, f prime is decreasing, which means f double prime has to be negative, right. So, if f double prime is negative, then f prime is decreasing, which means at that point you have a maximum. So, this is called the double derivative test. On the other hand, if double prime were positive, then the critical point will be a minimum. Okay. So, this is called the second derivative test. You might have seen it before, but this is a justification for it. So, clearly we are able to establish that a by b, this function hits a maximum. Okay. So, we have other such problems here. I am not going to do these in full detail for the interest of time. I will encourage you to solve it yourself. Let us look at e power x plus e power minus x. We remember the plot, right? E power x goes off like that, e power minus x falls down like that. If you add these two, what will happen, right? It is an interesting question. Okay. So, at 0 for instance, I am going to get 2. Okay. What happens when it increases beyond 2? Is 2 a critical value? Is there any other critical value here? You have to take the derivative. If you take the derivative, what happens? You will get e power x minus e power minus x equals 0. Okay. So, the only critical point that you will get here is when x equals 0. Okay. And that is the minimum point. Okay. The minimum value of this will be e power x, will be at x equal to 0, and that will be 2. How do you do? How do you check it? You can take a double derivative if you like, and you will see that at x equal to 0, it will go positive. So, maybe this alone I can quickly do. This is an easy problem. Okay. So, you have e power x, I am sorry, f of x is e power x plus e power minus x. Okay. So, if you differentiate, you are going to get e power x minus e power minus x is 0, and that is the same as e power x equals e power minus x, which is 1 by e power x. Cross multiply, e power 2x is 1, which implies 2x is 0 or x is 0. Okay. So, x is 0 is the only critical point, and you can argue around this. So, see, if x is 0, this is 0. If x is positive, this is going, so you can argue, like for instance, e power x is minus e power minus x is, this guy is greater than 0 if x is greater than 0, equal to 0 if x is equal to 0, and it is less than 0 if x is less than 0, right. If x is less than 0, e power minus x will be greater, this will be smaller, it will go negative. So, what is happening to this f prime of x? This implies f is increasing, f is increasing, and here f is decreasing. Okay. So, f is decreasing for negative x, reaches a minimum and increases again. So, this corresponds to a minimum. Okay. You can also do a double derivative test if you do not want this nuanced argument. What happens to the double derivative? you will get e power x plus e power minus x, and this is equal to 2 at 0, right. So that implies f double prime of 0 is 2 and that is greater than 0. So, it is positive, which implies minimum. Okay. So, this is the argument for why that has to be true. Okay. So, nice little function here. Here you have another function e power a quadratic. Okay. Notice, see, remember, the important thing to remember is e power anything is an increasing function of that quantity. Okay. So, the only way in which this x squared minus 3x plus 2, for instance, is a parabola which will look like this. No, it will go off to infinity for low x, infinity for high x, and it will reach a minimum. It will reach a minimum at some point. You can even figure out what that point will be. It will be, you know, if you differentiate this, it will be 2x minus 3. So, 3 by 2, it will reach a minimum. And what is e power anything? E power anything, you have to find the minimum of what is inside that, isn't it? That reaches a minimum at 3 by 2. So, e power that will also reach a minimum at 3 by 2, because e power x is like an increasing function. No, as x increases, it will only increase. Okay. So, that is the way to sort of intuitively argue this. So, minimizing this quantity e power any function is the same as minimizing the f of x function. Okay. So, that let me write that down in some way. You can also prove it using derivatives. I will come to that. Minimizing e power f of x is equivalent to minimizing f of x. Okay. This is generally true. Okay. So, you find the minimum of f of x, you would have minimized e power f of x also. Okay. So, in particular, if you look at this particular function e power x squared minus 3x plus 2, if you do f prime of x, you are going to get the same thing, right. I am using the chain rule, right, e power x times the derivative of this guy, and that is e power x squared minus 3x plus 2 times 2x minus 3. So, this quantity is greater than 0, right, for all x, and if it is, this has to be equal to 0, x has to be 3 by 2. Okay. And why is that a minimum? You can see, you know, you can differentiate it once again, you get minus through negative. So, this is a minimum. I mean, sorry, differentiated once again, you get 2, which is positive. So, this is a minimum. Okay. So, I hope this part is a little bit clear. You can check this again. So, generally, I think this rule is very interesting and nice. If you minimize f of x, is the same as minimizing e power f of x, right? So, because e power x is an increasing function. Okay. So, the other way is also you can write it, like, for instance, if you want to do e power minus f of x, okay, if you maximize f of x, you will be minimizing e power minus f of x. See, same as maximizing f of x. Why is that? Because if f of x becomes really large, then e power minus f of x will become the smallest, right? So, these kind of equivalences using the properties of whether e power x is increasing or decreasing, very nice and simple to do. Okay. So, think about it. This will simplify your work, help you to understand. Okay. The last one I am going to skip. I'll leave this as an exercise. Finding maximum minima is just differentiation, and this e power minus x squared will never become 0. So, you can pull it out and you will get values for x. Okay. So, that is that problem. Okay, let us close with this last couple of problems which are about inequalities. So, quite often this e power x is used for approximating complicated expressions. So, look at this expression here, product k equals 1 to 23, 1 plus k by 365. Okay. So, it is a complicated product. I want to get a sense of how this product behaves as k. Okay, what is its behavior with respect to k? You know, from this product, it's not at all clear to me. Is it growing with k? How is it growing with k? Is it close to something with k? I mean, I don't get a sense of how that function is behaving. For most of these kind of quantities, you can use this powerful relationship between e power x and 1 plus x. Okay. So, it turns out this e power x is greater than or equal to 1 plus x for all x. So, this is a very useful inequality to have. Okay. Let me plot very quickly how e power x is going to look. Okay. So, e power x is going to go like this, right? Let us draw it in blue. You know, this is how e power x behaves, right? Okay, it does not go to the left, but e power x. Let us draw 1 plus x. Okay, so 1 plus x will look like this. 1 plus x will look like this. What this inequality is claiming is e power x is greater than 1 plus x for all x. Okay. Now, e power x is 1 plus x squared by 2 factorial plus x cubed by 3 factorial, so on, right. So, for x greater than 0, if x is positive, e power x is clearly greater than 1 plus x. If you can put equal to also, right. So, if e power x is greater than or equal to 1 plus, why? Because these guys are positive, right. For x positive, these guys are all clearly positive. So, it turns out, and if if x is less than minus 1, what happens? If x is less than minus 1, right, 1 plus x is less than 0 and e power x is always positive, right. So, that implies e power x is greater than or equal to 1 plus x. That is also easy, right. So, this part is easy, this part is also easy. Do you see that? So, the tricky part is only this part lying between minus 1 and 0, x equals minus 1 and 0. Okay. So, what happens when x is, what happens for minus 1 less than x less than 0, right. This is what we have to figure out. Okay. For these kind of things, there is a little trick here. You look at this function f of x equals e power x minus 1 minus x. So, I want to look at the question of what happens for x between minus 1 and 0, or generally any x, right. What happens for any x when you want to compare e power x versus 1 plus x. One way of doing it is to look at the difference of these two functions. F of x equals e power x minus 1 minus x. Okay. So, notice what we can do here. This function, if you look at it, how to understand this function, you first understand its critical values, right. So, you differentiate it, you get e power x minus 1 equal to 0, and this happens only at x equal to 0. So, maximum or minimum can occur only at x equal to 0, there is no other value. At x equal to 0, is it a maximum minimum? How do you find that out? Okay, so first let us figure out what happens at x equal to 0. F of 0 is simply 1 minus 0, which is 0. So, f of 0 is 0, and at 0, does f of x hit a maximum or minimum? That is the question. For that, you can do the double derivative test. If you do f double prime of x, you simply get e power x, and that is equal to 1 at x equal to 0, which implies the 0 is a minimum. Okay. So, notice how I am going to use maxima minima to argue for a comparison between two functions e power x and 1 plus x. I am taking the difference of these two functions and I am showing the minimum possible value of f of x is 0, which means what? F of x is greater than or equal to 0 for all x. Okay. Okay. This function f of x, e power x minus 1 minus x, is greater than or equal to 0 for all x because that function has only one critical point, and at that critical point it hits a minimum which is 0. At all other points it is greater than or equal to 0 because it is a minimum, right. So, there is no other value below that. Okay. So, I hope this is convincing to you. So, this way you can use calculus and minimum and maximum and derivatives to prove inequality. So, this shows f of x is what? E power x minus 1 minus x is greater than or equal to 0, which is the same as e power x greater than 1 plus x for all x. Okay. So, this is a very nice result, e power x greater than 1 plus x, and you can use it to lower bound these guys. So, let me quickly show you the lower bound here. 1 plus k by 365 is less than, I am sorry, did I get this right? Maybe I can upper bound this, I do not know, is lesser than e power k by 365. Say upper bound here or lower bound here? Okay. Okay, so this lower bound I think is maybe not correct. Let me just say bound, whatever bound you get, let me not commit to lower bound or upper bound. Okay. So 1 plus k by 365 is less than and strictly less than e power k by 365. So if you do that, if you do a product of k equals 1 to 23, 1 plus k by 365, this is going to be less than product of k equals 1 to 223 e power k by 365. So notice what can happen here. So when you do product, I am doing e power 1 by 365 times e power 2 by 365 dot e power k by 365, and that is the same as e power 1 plus 2 plus so on till k by 365. Sorry, it's not k, it's 23. So notice how this becomes very easy. So now what is 1 plus 2 plus so on till 23? That is e power 23 into 24 by 2 by 365. So you get a very simple e power expression. So whatever that is, 23 times 12, that is 230, 254 e power 254 by 365, and you can evaluate. Okay. So you can also keep it as a general variable instead of 23, but you see here how this 1 plus k by 365, which is a complicated product, became a very simple number e power 254 by 365. Okay. So this is possible through these kind of inequalities, and this is a powerful way in which exponential functions are used for bounding very unwieldy expressions involving 1 plus x and all that. So I'm going to stop here. This e power minus x, these two I will leave as a exercise for you. This is very easy. This is just a very simple change of, let me not say very easy. This is a simple change of notation here. Instead of x, if you put minus x, you will get this guy. Okay, e power minus x is greater than or equal to 1 minus x for x between 0 and 1, and then you can use it to bound this 1 minus k by 365 as well. Okay, so we'll stop here. I hope in this lectures you've seen and understood the exponential function, how powerful it is in various different mathematical models, how you can construct very interesting looking functions, how you can analyze maxima, minima involving exponentials, how you can use exponential bounds for very complicated expressions, and how to evaluate limits using exponentials. All of these things are extremely useful, and I hope you understand and appreciate the exponential function. It's derivative, it's all itself, it's so smooth and nice, and yet it satisfies very simple, elegant properties. Okay, thank you very much.